if you know, is going to be numeric solutions of differential equations. Okay, so we started talking about that the other day. I'm not going to say anything further about just the overall by hand mechanical solution stuff that we've been doing thus far. You'll need to know some of that, but you won't be doing that so much on the project. It's going to be sort of more numeric type of things. And the way it'll be structured probably, again, we'll talk about this more Thursday, but the way it'll be structured is probably 5 or 6 sort of sub-problems, which are maybe all not related to each other, but they're sort of application-related problems. And we're going to take a look at an example of one such thing here today. All right, so we've talked about this plenty, the non-homogeneous differential equation, constant coefficients, all that sort of stuff. You know, essentially we call it x of t our input, y of t is our output, right? Somehow this corresponds to some sort of a circuit. We talked about our basic solution approach, so figuring out the transient, the non-homogeneous, which is the particular, right? Putting those together with the initial conditions to get whatever's left, whatever unknown coefficients we have. Always 3 steps, whether it's first order, second order, 1000th order, right? It's the same basic approach. We stopped basically at second order systems. We've talked about first order and second order systems. Just based on the fundamental principles of the universe, which you know, again, only become obvious to you once you've done enough of these problems, there really are only 2 types of systems in the world, first order and second order. Even if you have a 1000th order system, in general, it's pretty much just going to look like it's first order or second order. All right, and that's kind of based on what the specific roots of the characteristic equation are, right? Those roots kind of determine whether it looks first order or second order. Okay. I'm not going to say a whole lot about that. That's something that you'll deal with in later classes. You take controls and systems 2. You talk about those sorts of things. Okay. All right. So basically, for our second order thing, in summary, right, we ended up with 4 different options for what we could have, right, for our transient response. It could be undamped, could be underdamped, could be critically damped, could be overdamped. All right. The one thing I say is this one, in my mind, critically damped is sort of stupidly damped. I say that one's really kind of impossible to have. It's unlikely I would ever give you a problem where that is critically damped. The reason for that, you notice that's the weird one here where I have this little T in there, right? And that's done to make a unique solution. I probably will never have that. The reason for that is to get 2 roots that are exactly equal to each other like that is almost impossible to have happen in the real world. Okay, without some sort of active control. It's actually probably easier to have happen than this is. Okay. All right. Anyway, I want to move on from that. You guys should have enough at this point, especially, you know, you go back through the lecture videos and everything. You guys should know how to solve the first order and second order stuff by the time you're done homework 5 that you got right now. Okay. All right. So what we started talking about the other day was this idea of how I discretize an equation. And the sort of motivating example I gave is if I have some sort of digital control application. All right, so in the example I've got sort of listed up here, what I have is some sort of a motor with a sensor that's able to read the speed. So in this particular case, omega means the speed. All right, so somehow I'm reading the speed of this motor and I'm trying to control the speed of the motor. So what I might be saying here, I don't know, let's say I'm saying I want this thing to move at 50 radians per minute. Not radians per minute, revolutions per minute, right? And so what I want to do is I want to have a system that actually makes sure that this thing goes 50 revolutions per minute, okay? So what I have in here, this box is essentially is basically code for the most part, what's inside this. So code that basically goes through and says, all right, tell me what the speed is. So this would be a speed measurement right here. So tell me what the speed is and compare that to what I want it to be. And then basically tell the motor what to do. So this code in here tells the motor ultimately what to do. So out here, so the reason this box exists is basically this over here is sort of the digital domain. This is the digital. And then over here, I have the analog domain, the real world. All right. And so what's going on is I would have code here. And one of the things I said last time, if this guy's a microcontroller, he is going to be clocked, right? I mean, there's a clock inside of this thing, right? So if I have a clocked device, then how often do I perform operations inside that microcontroller? However fast my clock runs, right? So if my clock is a 1 megahertz clock, I'm only doing an operation at every 1 microsecond. Okay, now, that's a slow microcontroller if I have a 1 megahertz clock. All right, but you guys get the idea. So what that means is, if this motor over here is being controlled digitally, ultimately the model from my motor is something like this. Now, I talked about that very briefly last time. All right. So J d omega dt equals this expression right here. Now let's see if you guys remember, where did I say that came from? What is that an expression of? Anybody remember? It's related to momentum, yeah. So Newton's second law, right? Newton's second law, basically, which actually is directly related to momentum, but it's saying that this basically, Newton's second law, as you remember, it probably is F equals ma, right? Force equals mass times acceleration. It is, because this relates to force is the derivative of momentum. There's some things that go into that, but yeah, essentially what I have is that, J times d omega dt. So what is this? This is moment of inertia times the rate of change of angular speed equals the net torque, is what this is. All right, now without getting into the physics of that situation, I don't really want to get into the physics. This is the net torque. This is the torque produced by the machine. And this is the torque that is basically trying to slow the machine down. So it kind of makes some sense if you think about it. There's a torque produced by this thing that's related to the current that the thing has going through it, okay? All right, so again, I don't want to get into the physics of that too much, but basically what I get is a first order differential equation, all right? That first order differential equation describes how that motor works. And basically that's what the motor is doing, right? I mean, the motor is basically in the real world playing that equation out. If I wanted to be able to model this system, so I could say, well, if this thing works, I want the final speed that this thing reaches and the speed that I commanded to be exactly equal to each other. That's what a control system should do, right? If I want the thing to go 50 RPMs, it should go 50 RPMs, right? Well, let's say I needed to do that in less than 0.01 seconds. Well, if I need to do that, then I need to design this system. And so I'm going to need to find some way to make my analog world and my digital world agree with each other, right? I need to come up with some way to design that system to make that happen. And so what I need to do is ultimately take the analog world into the digital world to make that happen. And that's actually not that hard to do. All right. Now, so I'm going to describe a little bit of what we talked about last time and go into some more detail on that. All right. This is basically what we would do for control, but it's also what we would do if, let's say, one of the problems that you're going to have on the project is going to be a problem where essentially what you're doing is you're taking a look at designing an IC, designing a digital IC. And so basically what you're going to do is you're going to take a model and you're going to discretize it. And basically you're going to be making a simulator, a circuit simulator that's going to simulate what that circuit's going to do. All right, so there's a lot of things that you can do with this, but anytime I need to deal with a computer needs to take an equation like this and turn it into discrete time form. All right, and so we're going to define a couple of terms here associated with what I'm talking about. I've used this term discrete time a couple of times here. So I need to talk about what that means. All right, so we go back to the definition of a derivative. All right, so this was Newton's definition of a derivative. Basically said, I take the limit as delta t goes to 0 of what effectively amounts to the slope, right? So if you guys remember, if I have a function y of t that looks like this, right? And here's y of t plus delta t. This guy would be y of t. And I'm trying to take the slope between those 2 points, okay? And if I want to get the slope at some instantaneous point on this thing, I got to make the delta t here. That's the time between those two things. That's my delta t. I have to make that delta t. In Newton's terms, I got to take the limit as delta t goes to 0, which means I got to make it infinitesimally small. So small that it's not even there. Now, from a practical perspective, right, if I had y of t like this, right, and I wanted to put y of t in a computer, how small can delta t be?
As small as the computer can handle it, which is some of
As small, yeah, well, so it's a good answer. As small as the computer can handle, right? What's that? Well, so clock cycle is a good thing, is an important point. It's not really related to this question. It's data size that really matters. So the clock cycle thing matters as well, right? But the question is really how many points can I put into the computer? How many points can I put into the RAM of the computer? All right, we're going to address that question because one of the things that I saw people hit a lot of issues with on the project is they would try to create things that was bigger than the RAM can handle. All right, and the result of that is a blue screen or some sort of a crash of your computer. All right, so you have to think a little bit about how you're going to do this. Okay, but effectively that delta t can only be small, as small as it needs to be. All right, so we're going to get to that point. It needs to be as small as it needs to be. That's you guys don't like me saying that kind of stuff, but in other words, that means I need to think about how small to make it. Right, I can't just make it arbitrarily small. All right, and we'll see some examples as we go through today. All right, so but it's a question.
I've got a question. So I don't know if this is right. Now that we're on it, I just wanted to ask. Like, I always figured the differential t had to be like relatively small, not like exactly small, but like relatively small to the function size and stuff like that.
Well, you know what you just said is a very smart way of saying it, right? And from a practical perspective of putting it into a computer, that's exactly right. It needs to be small enough relative to sort of the function, the features, I call them, in the function. To be able to derive the properties of calculus, Newton needed to derive the limit and define the limit. Now, the unfortunate thing is, had Newton had a computer, we probably wouldn't need calculus. Calculus is pretty useless once the computer comes along, because I can just say, well, make delta t small enough, and then I can just make the computer do all the derivatives, right? But to be able to functionally define calculus, you needed this definition.
Nice.
Yeah, it's a good question, right? So we're gonna explore that question a little bit further as we go through today, right? Basically, what this says is, if I wanted to compute dy by dt myself, I could do the limit there, or I could just say, well, it's approximately, right? So when I do those squiggly equal sign, that means I'm talking about an approximately equal to. So I have a y of t plus delta t minus y of t all over delta t. All right, that is what I think of as sort of the approximate version of this. And sometimes I say this is discretized, because what I mean, the word discrete will mean that I have sort of finite steps that I can take. So what I've done is I have taken y of t and I have discretized it. All right, so that means that I have values at y of t equal to, so I said I have values of y of t at y of 0, y of delta t, y of 2 delta t, right? Y of 3 delta t, right? So on and so forth, okay? And delta t needs to be a small number. And the question is, it's all relative to the function itself about how small delta t needs to be, okay? All right, so we're gonna try to work out how we would take a first order equation, really any order equation, and turn it into something that we can utilize in sort of that computer digital framework. Now, last time somebody out there in TV land was talking about Runge-Kutta methods and things like that. There are other ways of discretizing equations other than what I'm doing here, and they actually yield better numeric results. But they don't necessarily lend themselves to sort of implementation in, let's say, real-time computation. All right, and the reason why I'm kind of focusing on this is, for one, the method that we're using is defined in section 7.5 of the textbook. That's one reason. All right, the other reason is it does align well with how you put stuff into microcontrollers and implement things in real time. Okay, so there's a reason why I'm doing it that way. So let's say I had this circuit right here, right? I would get essentially something that looked like this equation, where Y is the voltage across the capacitor, X is the voltage coming in, and I get a Y of 0 as my initial condition. All right, so I want to put that guy in the computer, so I have to discretize it. I have to go through that process. All right, so what should I do here? How should I start? Tau times what? What? Okay, y of t plus delta t minus y of t all over delta t plus y of t equals x of t. All right. Now, the way that I'm going to think about this is basically like this. I have stuff at time t, and I have stuff at time t plus delta t. Delta t, or time t is what I'm going to call now. All right, time t equal to 1:29 p.m. is now. Time t plus delta t is where? Soon. I feel like it's going to be like Spaceballs here all of a sudden. It's now it's soon. This is the future. Right? It's somewhere slightly in advance of where I am. Okay. So t plus delta t, I want to basically try to predict what's going to happen at the next time step. All right. So what I've done essentially from this is, yeah, this is calculus, right? So if you think about this, this is calculus. What is this over here? Algebra. Okay. Basically, y of t is the value right now. X of t is the value right now. Y of t plus delta t is the value of the output in the future. Okay. I can solve for those things just like they're variables. Okay. So what I'm going to do is, this guy he sort of becomes messy looking because the tau over delta t. I don't like that. So I'm going to define here A equals tau over delta t, like that. Okay. That's how I did it. How did I define it in my mind? Tau over delta t. Yeah, I'll call it tau over delta t. All right. All right. So I'm going to rewrite this as A times y of t plus delta t. Actually, let me look at how I defined it in my code. Or do I not have it in my code? Do you have it? Tau over delta t. That's what I thought I did. All right. Sorry. All right. A is tau over delta t. So what I'm just doing is rewriting this top expression like this. Minus y of t. All right. Equals x of t minus y of t. Right? I'm basically just performing some algebra to get y of t plus delta t by himself. Okay. And so again, this is sort of algebra here, but basically what I'm going to end up with is ultimately y of t plus delta t equals x of t minus y of t over a. Let's see, I'm trying to do too many steps at once. So x of t minus y of t over a plus y of t, like that. All right. If you guys look at that, what I did, so I basically brought a times y of t over to the other side and divided both sides by a. And I ended up with that expression. Okay. So you guys should follow what I did there. But basically what I've got is just an expression now, all right, for what my final result should end up being. All right. So I wrote an algebra equation that says, how do I solve for y at the next time step if I know x and t, or sorry, x and y at this time step? If I know x and y now, then I can figure out y in the future. All right. That's the basic idea. All right. So this expression is what I ended up with there. So this guy, that's why I'm just, yeah, okay. This guy is what I ended up with. So on the previous slide, I wrote it as x of t minus y of t divided by a plus y of t, where a equals tau over delta t, okay? So those two things are the same, okay? So what I want to do here is I want to say, well, all right, I need to be told y of 0. In other words, I always need to be told an initial condition. Anytime I'm doing differential equations, I always need to be told an initial condition. All right, so what I'm going to do is I want to use this expression now to try to figure out how, if I'm given y of 0, given the initial value, I want to be able to figure out, well, if right now is time t equal to 0, how do I figure out what's going on at time t equal delta t, right? Well, so I basically go into this equation right here, and I say, well, at time delta t, I plug in t equal to 0 to this expression, right? So I get that y of delta t has to be x of 0 minus y of 0 plus tau over delta t, y of 0, all divided by tau over delta t, like that, okay? Now, if I wanted to figure out what y of 2 delta t is, in other words, at the second time step, right? When would I compute that, first of all? At what time would I compute the value at 2 delta t?
At 1.
Well, yeah, at the first time step, basically, at 1 times delta t, right? So I would basically plug in t equal to delta t, and I would say y of delta t plus delta t, or y of 2 delta t, right, is equal to what? I would put x, whatever value it has at delta t, minus whatever y value is at delta t, plus this scaling times y of delta t, all over that, okay? All right, and if I wanted to keep going, then I would say, well, at t equal to 2 delta t, I would compute the value that I would have at 3 delta t, right? And that would simply be what? How would I write that out? What would I have on top for that? X of what? Yep, x of 2 delta t minus y of 3 delta t plus tau over delta t times y of 2 delta t. All right, that should be a 2 delta t there. All divided by that tau over delta t. So if you look at that kind of, and you back up and you try to generalize that expression, right? It's a big expression, but if I try to generalize it, what I see is what? I basically see that the y value at the next time step always depends on what? The y value at the previous time step. That's basically the derivative happening, right? So if you think about what's happening, right? If I have a circuit, let's say I had this circuit, right? What it's saying is that the voltage on this capacitor depends on both the input and past values of the voltage on the capacitor, right? That's basically that's what this expression is sort of saying, is the value of that voltage depends on both previous values of the voltage as well as on whatever the input is, okay? So I can generalize that and say, well, if I'm looking at the nth time step, right? The value of the capacitor voltage, the value of the output at the n plus 1th time step, the one right after right now, is equal to these, or depends on the values that I have right now, okay? So in words, what this says is the value of the output one step ahead of me depends on the output right now and the input right now, okay? So you can actually come up with some cleaner ways, or not necessarily cleaner ways, I don't want to say it that way, but you can come up with some other ways to represent this and write this expression, all right? That might make it look a little bit cleaner, but less obvious for maybe how to code it, okay? So where we ended last time is that, you know, this guy, is a very simple thing to code up, right? Because you basically think about it, well, I'm going to compute the values at the next time step. And then I'm going to go to the next time step and use the value that I just computed to compute the next one and just keep rolling through that loop, okay? So this is a pretty easy thing to do. It's a recursive relationship, right? So it's pretty easy for me to basically create this with some sort of a loop. Other thing I want to point out about this is I could write this guy like this, right? So what's different about that top expression and the bottom expression that I wrote there?
M represents delta t.
Well, you're kind of right. Basically, what I'm trying to say is do I have time represented at all in the bottom expression? Is there any t? Well, yeah, sure does look like that. No, yeah, it does. What I'm basically trying to represent with the bottom expression is how is y going to exist, and how are both y and x going to exist in a computer as an array, right? They're going to be an array of numbers, right? That array doesn't necessarily have a time associated with it. It's just an array of numbers, right? If you went into C and you created an array, that array is just a series of numbers in an array. They're just in a series of sequential memory locations, right? So what I'm doing is saying that I don't need time necessarily to represent y. I can represent y as just an array. And if I do that, it's saying that the next entry in the array always depends on the previous entry in the array, right? And so it's not per se that delta t is equal to 1, right? It's just to say that the entries in the y vector have this dependency on the previous entries in the y vector. Well, you're right. Delta t also matters if I want to look at the function, right? If I want to plot the function, then I need delta t to be able to know what it looks like. Okay, and we're going to see the significance of that with some examples. Okay, so what this ultimately amounts to is if I have values of a function at a particular set of times. In this case, my delta t is basically 0.001 seconds, right? So 2 delta t is 2 milliseconds. 3 delta t is 3 milliseconds. 4 delta t is 4 milliseconds. 5 delta t is 5 milliseconds. What that means is I have a corresponding n value, right? So a corresponding entry into this vector that I'm creating. So if this was the value of the actual function at that time, this is the value that goes into the array. So the way that I kind of think of this, all right, is to say that if I had this function that's written here as x sub c of t, all right, we're going to talk more about this for the second project. But if I have this function x sub c of t that exists in the real world, and I had a device that was able to bring that guy from what I call continuous domain to the discrete domain, what I end up with is just a series of entries which have been picked off of that function. Right? That's really what an analog to digital converter does, is it takes some function that's smooth and continuous and it picks values off at regular samples. All right. And that's really what we're doing. Now in this project, we're not dealing with analog to digital converters directly, right? You're not actually handling an analog digital converter. We're thinking about the concepts that go into it, right? And what we're doing, it's sufficient for you to say, well, I want to be able to pick values off of that real world function to be able to do this, okay? Now, the way I would code this, one way to code this is something like what I have right here, okay? Where what I've done is I've somewhere defined a delta t, okay? And apparently I'm going from 0 to 1 second in steps of delta t, all right? And again, we're going to talk here in a couple of seconds or a couple of minutes about how we figure out what delta t is. All right, but then I have a for loop that basically goes, now notice it goes from 1 in steps of 1. You don't necessarily have to tell MATLAB that you want to go in steps of 1. If you don't tell it that middle number, it goes in steps of 1. All right. It would have just assumed that, right? If you want to go in a different order, then you got to tell it that, but it's just going to assume that you want to go in steps of 1. I always write it that way. All right, so any of my code, you'll always sort of see it that way. All right, now notice I went from 1 to length of t minus 1. Okay. Now, what I did here is I have an if statement that checks to see if n is equal to 1. Why do I have to have an if statement that checks for n equal to 1?
Because you have to handle the initial condition.
I have to handle the initial condition. So if you think about that, when n equals 1, now this might be a little bit confusing for you because when you look back at this expression I had here, right? What would correspond to t equal to 0? What value of n, this expression, what value of n do I need for t equal to 0 in this expression here? N equal to 0, all right? What do we know about indexes in MATLAB arrays though? They start at 1, all right? So if you look at that, I've basically said when n equals 1, so the first time I run through this array, right, y of 1 is equal to my initial condition. Okay, so somewhere else in my code, I said that y sub 0 like this is equal to my initial condition. All right, we gave it a number. Well, again, we're gonna do an example in a minute. Then basically what I did was I took this equation and I basically implemented it right there. All right, where I had a somehow is equal to that tau over delta t like that, okay? And I just loop through this. Now, you're gonna have to think carefully, the stuff that'll cook your noodle later, right, is when you think through things like, well, why did he go to t this minus 1? All right, you guys are gonna have to think about that stuff a little bit more as you go through this, right? But the approach, if you follow the approach, that's the basic concept of what we're trying to implement. All right, everything is best seen with an example. So let's do an example, right? So I've got an RC circuit that has this equation here. So basically what I'm saying, the capacitor voltage is given by this differential equation. I've got an input source that is 4 cosine omega t. And what did I say? I say 4 cosine omega t times u of t. What does the u of t mean again? It's a unit step. So in the context of this problem, what does that mean if I had a circuit? Yeah, it means that cosine source turned on at t equal to 0. And I was given an initial condition here that y of 0 is equal to 10 volts. Okay. All right. So I want to discretize that equation. Okay. So to do that, I guess maybe I'll do that here on this slide. So what do I need to do, right? I'm going to say that I have 0.01. All right. dy by dt needs to become an equation. All right. So what do I do to dy by dt here? What's on top? Over delta t. All right, so I have that plus y of t equals, I'm just gonna call it x of t, all right, to keep it simple. All right, where my x of t is 4 cosine omega t for t greater than or equal to 0. Okay, all right, so if I go ahead and rearrange this whole equation and solve for it again, I'm going to get y of t plus delta t. All right, and I don't want to go through and solve this guy again necessarily, but I get y of t plus delta t becomes y of t plus, or no, x of t minus y of t. What is it? Plus 0.01 divided by delta t times y of t all over 0.01 divided by delta t, like that. All right, so I get that result. Okay, now I got to code that. So here's code that does it. Okay, so let me make this a little bit easier. Let me, can I? Copy this over. All right. Let me take this equation and put it next to my code here. Okay. All right. So back to full screen. Okay. All right. So what I've done is I've defined everything from my previous slide. So y underscore 0, this was my initial condition. Okay. Tau is 0.01. Now I chose my delta t as tau over 1,000. Again, I'm going to do that right now without saying why I did it, but I did it. Okay. And then I defined for myself basically a time vector that I defined to go for a second. Okay. And I defined a y vector here. So I have this guy's zeros size t. What do you think that does? If I have a command zeros of size t, yeah. Makes an array of zeros that has the same dimensions as time. All right, so it's going to be a row vector looking like time, except every entry is going to be a 0. And then I created this guy here, x. All right, I created my input vector. Okay, and omega is defined somewhere else. Okay, all right. Then I basically implemented this graph here and made a plot of it. All right, and so the question is this: how do I decide what my delta t is going to be? How do I make a decision about the delta t? So let's think about this before we do it. What is the solution? We have a first order differential equation. Y of p plus yc. That is always what our solution is to a differential equation, always. Okay? And it's first order. So what does this guy look like? What's in the solution to y of t for this problem? So let's go back. All right. So this is where now, at the end of it's the kind of thing I say all the time. 10 years from now, I see you guys on the street. You're not going to remember how to solve a differential equation, right? I know a lot of engineers that I went to school with. They're very good engineers. They have a lot more money than I do, and they can't solve a differential equation. Okay. The question is the intuition of this thing. What do I should be able to know what the output's going to look like. Okay. So if I gave you that differential equation, you're going to have a steady state solution and a transient solution. What's the transient solution look like for this thing? An exponential. Okay, so I know that this guy is going to have an a e to the negative t over tau. I know that. Okay. What else do I know? What do I know about the steady state solution to this guy? It's going to turn into a cosine whose amplitude I don't know. What about its frequency and its phase? I know it has the same frequency as the input, right? I know it always has the same frequency as the input, and I know that it's shifted probably from the input in some way. So I don't know its shift, I don't know its amplitude, I know its frequency. So I know I get that, okay? So what I talked about before is, and I'm not sure who it was who made that comment earlier, but delta t needs to be small enough so that I can see the features, what I call the features of that waveform, okay? So let's think about this. What is a e to the negative t over tau? What does that look like? Yeah, exponential downward, and it better not be probably. It better be that it is, right? Because I'm only talking about physical systems. Well, an a e to the negative t over tau is only going to do this, right? I could have a step response that goes up, right? But the a e to the negative t over tau is always going down, okay? Always. And how long does it take him to go downward? Yeah, I mean, technically forever, but we say that by 5 tau or so, this guy is dead. So by the time he becomes dead, we say, I don't know, that sounds more negative, dead, right? But he's gone after about 5 tau. Okay. Yeah, he's gone to sleep, right? So now this guy over here, he has a period, all right? What's his period? T equals what? 2 pi over omega. Okay. Now, there is a theorem in the world that says, it's called the Nyquist sampling theorem. Some of you guys may have heard that term before. I'm not going to talk about it. The Nyquist sampling theorem is very idealized. It says, if I get at least 2 samples in a period, then I can perfectly reconstruct a cosine. Now, that doesn't really work out well in practice. But if I told you I wanted to see a cosine, and I wanted to see the full smoothness of that cosine, I want to see that cosine looking like that, okay? What would be your choice for the plot of that thing. We've made lots of plots of cosines at this point, right? What would be a reasonable choice to make sure I can see that whole thing?
Something at the beginning, something at the peak, something at the trough, or something at the.
Well, okay, so let's say let's say you chose points like this.
What is something at the.
What is so let me ask you this. If I did this, how does MATLAB, we talked about this at the very beginning. What does MATLAB do between those points? It draws straight lines. That doesn't look like a sine wave, right? So let's say what did I tell you at the very beginning about drawing a sine wave? If I want to draw the sine wave right, how have I always told you to set up your t vector in all of the graphs you've made in homeworks 1 through? Well, yeah, I usually do something like, well, t over 100 or t over 1,000, something like that. All right, that's kind of a delta t, isn't it? That's a time step that I gave you, right? That's kind of a delta t. All right. Now, why did I choose that? Well, I know if I have 100 points in a period, in other words, this means I'm going to graph 100 points in one period. If you think about that, right? My time step is t over 100. Then as I go through 100 points in my y vector, I will have seen one full period. Okay. Now, that is not all that scientific, but it makes sense, right? I need to have enough points to be able to see this thing. So what I have to do is I have to look at this and say, well, I have two things going on in my solution, right? I have this decaying exponential and I have this cosine waveform. And I got to figure out, well, this exponential is done in 5 time constants. This guy over here has a period 2 pi over omega. I need to figure out what is it that I want to see in my graph when I look at the graph. Do I want to see the transient and this thing? Then I got to think about which one is the smallest. All right. And when I say smallest, I got to think about which one is the smallest in time. All right. In other words, which one is the shortest on the x-axis. Okay.